In this video, we're going to consider the stability criteria for saturated parcels of air. This can be expressed in terms of the lapse rate of the pseudo-wet bulb potential temperature. When d theta SW dz is less than 0, the environment is unstable. When d theta SW dz is greater than 0, the environment is stable. And when d theta SW dz is equal to 0, then the environment is neutral. It's a little bit easier, however, to work out the stability of saturated air by comparing the environmental lapse rate to that of the saturated adiabatic lapse rate. So let's do that graphically. Here we can see have been marked in 3 saturated adiabats for reference, and now let's put in the temperature lapse rates for the environment. In the first layer, you can see that the environment cools more rapidly than a saturated adiabat. Gamma is greater than SALR. And so that's unstable because if you take a parcel of air that's saturated and lift it, it will be warmer than the environment. Layer 2, the environment cools more slowly than the saturated adiabatic lapse rate, so gamma is less than SALR. So anytime you lift a saturated parcel in that layer, it will be cooler than its environment, and it will experience neutral buoyancy, and therefore that layer is stable. And for the third layer, the environmental lapse rate is equal to a saturated adiabatic lapse rate. So if you lift a saturated parcel, it's always at the same temperature as the environment, so that's neutral buoyancy. You can then compare each of these layers to the lapse rate of the pseudo-wet bulb potential temperature. So for example, in the first layer, the pseudo-wet bulb potential temperature decreases with height. The temperature trace cuts across decreasing values of the of saturated adiabats, and so it's a unstable layer. In the second layer, the pseudo-wet bulb potential temperature at the bottom of that layer is less than at the top, so d theta SW dz is greater than 0, and that's associated with stability. And in the third layer, the value of theta SW is the same at the bottom and the top of the layer, and so that's neutral stability. But as I say, it's easier by inspection to compare the environmental lapse rate to that of a saturated adiabat and see whether or not the parcel is going to be warmer when it's lifted than its environment. So if the environmental lapse rate is between the dry and the saturated lapse rates, the stability of the parcel is conditional on whether it is saturated or not. So we can define conditional instability as when the environmental lapse rate is greater than that of the saturated adiabat, but less than that of the dry adiabat. Again, that's best shown graphically. So here we have 4 different lapse rates, A through D, and then we have a dry adiabat, a saturated adiabat, and an isotherm. So consider environmental lapse rate A. This is absolutely unstable because it doesn't matter whether or not you lift a parcel that's dry or saturated. As it rises along those lapse rates, it's going to be warmer than the environment, and therefore buoyancy force is upwards, so it's unstable. Environmental lapse rate B is between the DALR and the SALR. So if you lift a dry parcel, it will cool more rapidly than the environment, and since the parcel will always be cooler, it will be stable. But if the air is saturated, then as you lift it, it will be warmer than the environment. So the stability of environmental lapse rate B is conditional on whether or not the parcel of air is saturated or unsaturated. Finally, lapse rates C and D. Well, you can see that if you lift a parcel that's either dry or saturated, it will be cooler than either of those environmental lapse rates, and therefore that region is absolutely stable. It doesn't matter whether or not parcels are saturated or unsaturated. Here's the first of our examples. So by inspection, determine the instability of each of the indicator layers of the trace, and then assess whether or not you think, as a whole, this trace is likely to produce convection. Stop the video now and make that assessment. So how did you go with that? What we can see is the answers are provided there. The lowest layer is a dry adiabat, so it's conditional on whether or not the parcel is saturated, so it's conditionally unstable. The second layer is absolutely stable because it doesn't matter whether or not the parcel is saturated or unsaturated. And then layers 3 through 5, you can see by inspection, are all conditionally stable, unstable. 6 and 7 are absolutely stable. They represent inversions, and then layer 8 is conditionally unstable. Now what's been put in is the representative mixing ratio and potential temperature lines, and you can see that you can get a convective temperature that will produce a level of free convection, and Kate will be realised. It's not quite what's shown there, it's going to be a little bit warmer. So the convective temperature is the temperature which will provide parcels being heated to the level of free convection, and it looks very much like that will occur for this trace, and there's sufficient Kate then for convection to occur. Now here's an exercise. Determine the stability of each layer labelled on this trace. Pause the video and do this. So how did you go? What do you think? Well, again, layer 1, for this environment, you can see compared to the dry adiabatic lapse rate, it's stable, but for a saturated adiabatic lapse rate, it's unstable. We can argue the call with layer 2, but to me it looks neutral. 3 is absolutely stable, and 4 is an inversion, so that's definitely absolutely stable. 5 is conditionally unstable, so it's unstable for saturated motion. 6 is absolutely stable. Again, the temperature's not quite increasing with height, so it's not an inversion per se. And 7's conditionally unstable or stable. Will this trace convect? Well, it doesn't look like that it will really, not on the basis of surface-based parcels of air. There's too much convective inhibition for this environment.